Thank you, Robert. Welcome to everybody. So, it would be impossible to do full justice to Jean's many profound works in a month or even in 6-month period, let alone a couple of days of memorial in his honor. What we hope to do in these days, are to give, or have given, or somebody will give brief scientific talks to give a flavor of his genius as an analyst in the broadest sense. With this in mind, and as you can see, we chose, this is Helmut and I who organized this, we chose some experts to talk about some areas that John impacted with his problem solving and the tools and theories that he developed. Terry Tao, whose interests are close to Jean's, was supposed to be the first speaker. Unfortunately, he couldn't make it, and Avi and I will try to step in for him. Terry wrote a nice and informative obituary soon after John passed away, and I recommend that you all read that if you haven't already, and also read the comments after in the blog. Many of them are very interesting and telling. Terry sent me a short statement to read. In fact, since the family couldn't come and many others couldn't come, I'll be spending in the next today and tomorrow a lot of time reading appreciations by other people. So this is what Terry Tao had to say. I deeply regret that I'm unable to attend this event commemorating one of the most brilliant mathematicians I have known. Jean Bourgain opened so many doors in analysis and related fields that allowed others such as myself to explore and build their own careers. As a graduate student, the papers of John that I was assigned to read were the most challenging and frustrating that I had to work through. But in the process of patiently and carefully understanding all the steps and offhand remarks in these papers, these were immensely valuable to me, supplying me with a powerful array of tools and insights that have served me well ever since. I have heard by reputation that he was quite the competitive mathematician in his youth, but when I met him, he was always incredibly generous with his time and ideas. He produced prodigious amounts of first-class mathematics right up to the very end, and our discipline is very much the poorer for his absence. So my plan, and Avi will follow me, is to describe a few of Jean's work, especially the recent ones. As you all know, he was diagnosed with cancer some 5 years before he passed away. During this period, he endured harsh medical treatments, but thanks to his very positive and optimistic attitudes to mathematics and life, he produced some of his finest work during this period. He continued to do what he loved to the very end. So let me start with Vinogradov's mean value theorem. So now I get to describe some mathematics. This was a crowning achievement which I witnessed as it evolved. In a series of papers with Demeter and by himself on restriction and decoupling in harmonic analysis, Jean recognized the potentials of these methods from analysis to give highly non-trivial upper bounds for the number of integer solutions in regions which satisfy certain equations. So these are Diophantine equations, and you're trying to count the number of integer solutions in growing regions and obtain sharp bounds. When Bourgain and Demeter established what is known as the L2 decoupling theorem in 2015, about which we'll hear much more tomorrow from Larry Gruth, John was quite excited as he felt the Vinogradov mean value theorem, that I will describe in a second, or the mean value conjecture, was a conjecture at that time, was well in sight. And indeed it was, and he together with Demeter and Guth established the striking result a year later in 2016. So let me describe this theorem. I'm going to describe about 5 theorems and say a couple of words about them. So the equations are a system of equations, a linear equation. The variables are integers, x1 up to xs, y1 up to ys, s variables. And you have x1 up to xs equals y1 up to ys, and then the square, so it's clearly a moment type of problem. Up to the nth powers equals the nth powers. And you're interested in the number of solutions to those equations where the x's and y's are all at most n. This number, which is usually denoted in the theory of numbers as JSN of capital N, because the variables are going up to capital N, can be expressed as a multiple integral if you take the 2s power of that exponential sum there, that sum over j, and integrate it with respect to the alphas, which are variables running over the torus, 0 to 1, then that will actually count the number of solutions. So this is where analysis meets number theory. If you're trying to count the number of solutions by this method, you can write the number of solutions as an integral. And Jean, who can estimate anything that can be estimated, got interested in giving upper bounds. So the famous theorem that I was referring to, the celebrated theorem from 2016 of Bourgain, Demeter, and Guth, is that the following upper bound for the number of solutions, so little n are fixed, and capital N is getting large, and there's an upper bound of n to the s. Now this notation, less than epsilon, means that it's less than a constant times what's on the right-hand side, and that constant depends on epsilon. So Jean used to call that upsilon. When epsilon is an arbitrary small number in this, is to be understood in this notation. So you get an upper bound for the number of solutions, which is of the form n to the s, and then n to the 2s minus this quadratic expression n into n plus 1 over 2, and there's the extra epsilon. And there are already n to the s diagonal solutions if the x's equals the y's and permutations of them, so that is one part of the answer, and it's not difficult to see that the density of solutions is a second contribution. And so the remarkable statement is that you're getting a sharp upper bound for the number of solutions, which is very rare, a very rare achievement to be able to get a sharp upper bound. And this is really using analysis, decoupling, which I won't go into, and many, many other ideas that go into the proof. Now, this particular system of equations was introduced by Vinogradov, and he gave non-trivial bounds himself in his remarkable work giving the best results known towards the Riemann hypothesis. His zero-free regions for the Riemann zeta function are based on these, on upper bounds for the number of solutions there, as a technical ingredient at some moment. And the other thing where Vinogradov understood its importance is in what's called the Waring problem, and where he obtained rather sharp results. So Vinogradov already obtained non-trivial upper bounds, and Woolley, over many years, culminating in 2012, using his method of efficient congruencing, also obtained sharp improvements of Vinogradov, almost the sharpest results, but not quite the ultimate result. And his methods are not, now that we understand them much better, are not unrelated to the methods of Bourgain, Demeter, and Guth, but nevertheless, this achievement of Bourgain, Demeter, and Guth is very highly celebrated, and I know Jean was extremely happy with this, and you saw it coming over this period, as I said, 2016, 2017. These were actually very productive years in his career under very harsh conditions. I would like to actually now describe some other works from this period, and the next work is joint with Semyon Dyatlov. And let me read what Semyon wrote to me. He couldn't make it. I worked with Jean Bourgain on applications of harmonic analysis to quantum chaos in the fall of 2016. I'd come to Princeton several times before in the hope of meeting, but each time he was away due to his illness. I was really lucky to catch him there that fall. In the short time, he advanced the field of quantum chaos beyond what any of us would have dreamed possible. And it was a privilege for me to see Jean Bourgain in action. So now let me show you what they proved. So he came here. It's called the fractal uncertainty principle. It was formulated by Dyatlov. He saw exactly how this might be used, and he was stuck on something technical which was quite challenging, and he was asking around, and he knew exactly where to go, and that was the office up there in that building, until he found the person who was going to somehow solve this. And by the way, it didn't take Jean it wasn't quick. It took him quite an effort. A very important ingredient in this work is work of Malivan and Berling that Jean told me he's shocked he wasn't aware of this theorem in harmonic analysis. And once he became aware, he didn't say how he did, then this particular theorem started to take shape. So we all know the standard uncertainty principle. This is a fractal uncertainty principle, which says a function and its Fourier transform the function and its Fourier transform cannot both be localized on a fractal set. And one expression of that is through what they're calling porous sets. So they fix a number, nu positive, think of a very small number, and then an interval which is in 0, 1, where the alpha might be going to 0. And a subset of the real numbers is called porous, new porous. If for every subinterval of length in the interval of scales, call it J, there's a, call it I, there's a subinterval J whose length is nu times I, so it's that fraction of J, and that new subinterval J doesn't meet X at all. So porous means that you're missing out this, and this fractal sets have this property. And f hat is the ordinary Fourier transform. And the beautiful theorem, there are many versions of it, of Bourgain-Dyatlov, this fractional uncertainty principle, says that if nu is given and fixed, then there's a positive beta. A lot of Jean's theorems are they're constant. You never can work out these constants. They come out of a series of iterations, scale analysis, and ingenious ideas. But there is a positive constant, such that if x and y are new porous subsets of 0, 1, and h is a parameter which is going to 0, then for any function which is square integrable and no other condition on the function, if the Fourier transform is contained in H inverse of Y. So here Y is going to be a porous set. So the Fourier transform is contained in this fractal-like set. And then X is F restricted to X in position in the X space. The restriction of F to X must be very small. In other words, there's the H to the beta. Beta, remember, is positive. When H is very small, it says that F restricted to X is the L2 norm is a very small portion of the total mass. So it's a technical sound of theorem. It makes exact the statement of fractal uncertainty, and it's the key ingredient which opened this door that Dyatlov mentioned. Perhaps I'll give you an application just to show you concrete mathematical physics application, as he said, to quantum chaos or microlocal analysis. And this is an application of this theorem. Suppose I have a surface of negative curvature. It's drawn on the right there. Hyperbolic means constant negative curvature minus 1. And suppose I have an eigenfunction of the Laplacian of very high frequency. The eigenvalue is denoted by Tj squared. And the L2 norm of phi is 1. And suppose Tj goes to infinity along any sequence, and I take a weak limit of something called a microlocal lift. So if you take phi j squared times the area, I've normalized the L2 norm to be 1, so that's a measure on the surface. And you can lift that measure to a measure on the space of unit tangents to the surface, which is a 3-dimensional space, and you can take a weak limit. And that limit I'll call a quantum limit, or semi-classical quantum limit. And the theorem is that if you have an open, non-empty open subset in the space of unit tangent vectors, then that set will always be positively charged. In other words, an eigenfunction can't go to 0 on an open set. And you can imagine that there's a lot of dynamics, semi-classical analysis, and then at one critical moment, this fractal uncertainty principle is what ensures this is true. And it is the thing that makes everything tick. Okay, the next theorem I want to describe, also from this period, is about the Schrodinger equation. And it's about almost everywhere convergence for solutions to the Schrodinger equation. So I'm in Rn, I take a function in L2 and I solve the Schrodinger equation, which of course is unitary, so the solution uxt for each fixed t is a function of x, which I'll write as e to the I delta t. That's group keeps the f's that you get, or the u's for a fixed t, are in L2. And you can ask that when t goes to 0, in other words, that tends to identity, then the function should converge back, the solution should converge back to f, which of course it does in pretty much every sense you want. But what about almost everywhere? And it turns out it doesn't converge back to f everywhere in L2. And this question has a very nice answer. So you want to look at Sobolev subspaces. So these are subspaces of L2 where you've put some extra derivatives or fractional derivatives in this parameter S. And you want to know for which S is it true that the solutions converge back to F almost everywhere. And it's not surprising that someone like Leonhard Carlson would have started this activity, having proved one of the most striking theorems in analysis, and that's his almost everywhere L2 convergence theorem. So he's asking this question for the quantum group. And he showed that if S is greater than or equal to 4, then you have almost everywhere convergence. So if you're in the Sobolev space HS, you do have convergence almost everywhere. And soon after that, that was 79, Dahlberg and Koenig showed that, well, if S is less than a quarter, then it's not true. You do not converge almost everywhere for some function in HS. So there's some bad functions, or many of them, for which it fails. And quite remarkably, in 2016, Jean, who, the ... there for n greater equal to 2, there were many works on either side, but there was no even conjecture in the air as far as I understand. And then in 2016, in a 4-page paper, when you make an example, it's usually very brilliant. You just write it down, convincing, and you check the details. So in a 4-page construction, explicit construction, Jean shows that for S less than this number n over 2 to the n plus 1, which agrees with Carlson, of course, in the case of n equals 1, the answer is no. That is that you do not have convergence, or the maximal function is not bounded. And he suggests, he understands already that this number is important, it's probably sharp. This is 2016, and then that completely changed the landscape. By 2017, the case of n equals 2 was solved by Xiaomin Du, who was here last year. I'll say a bit more word about her in a minute, and Larry Guth and Lee. That is for S bigger than 1/3, which is the Bourgain number there. You will have almost everywhere convergence, and their methods don't so far work in higher dimensions, but Du and Raojing Zhang solved this completely for all dimensions when S is bigger than the Bourgain constant. So between 2016 and 2018, this problem was solved. Du and Zhang, two young postdocs here from last year, had come here to work with Jean. He was unfortunately not available, but they worked together without him and solved the problem. And he lived to see the answer, and they sent him an email with the solution, and they got a very nice reply. Very nice. He was at this point, the emails were very short, and that is very nice exclamation mark. So the problem is completely solved except at the exact value in higher dimensions. So those are the three things I wanted to describe from the most recent time. That's the period. But also during this period, he continued to develop tools and to prove new results, which were natural continuations of his work from the last 10 years, which was also extremely productive and fruitful. These include his works on Apollonian packings, which we heard was on this Baron insignia, which was done with Fuchs and Kontorovich, and on the Zaremba conjecture with Kontorovich, and the theory of spectral gaps and expanders with Gumbert, and many related Diophantine problems with Gumbert and myself, and with Rudnick on eigenfunctions on tori. These are the results I know best, so I mention them, but they're all in recent years, and they are all things he continued to work with in this period. We will hear some more about some of these, but I want to describe and finish my talk by some less famous results of Jean, but which are, I think, good samples of his raw power. So, I should be using that. But anyway. All right, so this is uniqueness for trigonometric series. There's a theorem of Riemann, so just watch here. Riemann, Cantor, Shapiro, and then Bourgain. So this is the history of this problem. Riemann asks the following beautiful question, and he answers it. Suppose I have a series, a Fourier series, E in Jean's world, in our world, E, I should have said this, it was on one of the slides, that E of x is e to the 2 pi I x, always. So I have a Fourier series of this type, some m less than or equal to m, a m e to the 2 pi I m x, goes to 0 for each x, then are all the a m 0. But there's no condition on the uniform convergence. It's for each x, it goes to 0 separately. So this is a very hard thing to work with. But Riemann was able to prove that then all the AMs are 0. In fact, what he did was he formally integrated twice to form the series that you see here, AM over m squared, m not 0, and then formally that is this integrated twice. Its second derivative will be back the other function. And when you integrate twice, this is now uniformly convergent series in dimension 1. And so you have a function and you have something to work with, and essentially he shows that the second derivative in the sense of distributions is 0, and hence all the AMs must be 0. Cantor extended this to show that if that's true for all x outside in a set K, where K is a closed countable set, then he can still conclude that all the AMs are 0. And then he had a contradiction on his hands, because what was left? You had 0, 1 minus this K. His proof worked. He had to invent cardinality to resolve the contradiction. This is why he came up with the theory of cardinality, was to resolve this contradiction in this Riemann-Cantor theorem. And so that's the uniqueness theorem in dimension 1. And Zygmunt, who was developing this theory in Chicago in the 50s, and his students popularized the problem of what happens in several variables. So you have Fourier series in several variables. Now you have m in Zn, and the absolute values of m are less than or equal to capital M. Same condition. Is it true that all the AMs are 0? And Victor Shapiro in 1957, though it wasn't quite complete and was completed by Cook in 1974, analyzing this function, but now this function is not absolutely continuous in higher dimensions, so it becomes much harder, but nevertheless they were able to prove the conjecture, the same theorem as Riemann's, that is that if that converges to 0 conditionally for all x, then in fact AM are all 0. But for n bigger than 2, it looked daunting and hopeless because this function was quite wild, it's not continuous. And enter Bourgain in 1996, he proves the theorem completely for all n in an amazing tour de force using bare category where the function's discontinuous and Brownian motion at the end to make estimates on sets of various capacity. And this led Victor Shapiro, who's the guy who made the first progress, to say the following, which I like very much, that had he not casually mentioned this 40-year-old problem to Jean Bourgain, the problem may have gone unsolved for another century. As you know, this comment applies to many of Jean's solutions of problems. I think he brought us many centuries ahead of where we should be. Okay, and then my final example is connected with my first time I met Jean, and the first time I had actually serious mathematical conversations with him, and that was at Caltech around 1987. We were both visiting there for a semester or a term. At some point, he asked me if I have any good problems in number theory, as he wanted to score. I said, score? He said, yeah, I want to score in number theory. Okay, I'd never heard that way of talking about proving theorems, but for him, he had the scoreboard, and he had not scored in number theory. Okay. So I think I teased him a bit by saying that the best problems in number theory typically have algebraic structure, and they may not be so suited to your taste. Anyway, I did think of something, and that was a conjecture of Hugh Montgomery, and I suggested it to him, and here it is. Let me state it. So you have everything he says in the real line. T is a real number. Tau is a subset between minus t to capital T. T is a parameter going to infinity. N is an integer going to infinity. Those are the two key parameters. And you have a one-separated set, that curly T is a one-separated set. That means that the points in that set are at least one apart. But you don't know anything else about the set. And Montgomery's conjecture is that for all epsilon, the usual notation as before, that this quadratic expression in the ANs is some t in t, some absolute AN n to the IT, it's the usual, everything is real n to the IT, absolute squared, is at most something times the sum of the AN squared, and that something is n plus t to the epsilon, tau, this cardinality of t to the epsilon. Again, n is the diagonal, and the capital tau is the off-diagonal. This is typical in these kind of inequalities. Basically, you're trying to understand the L2 norm of the matrix whose entry is n to the itj, where tj is in your set T, well-separated set, and the n is up to capital N. And the reason Montgomery's conjecture is so interesting is it has rather profound implications on the Riemann zeta function. For example, the density conjecture, but many, many other things. This was 87 when I discussed this with him, and then I didn't think about it, didn't hear for a long time. And 2 years later, I hear from him, it's false. And he shows, amazingly, that it's false, and that the best possible thing on the right-hand side here would have to have an extra fact of n to the half times t. And his counterexample is very elementary. Maybe it was a little unpleasant for some of us, or Montgomery anyway, to see the counterexample. But it came out of a deep understanding why it was false. So he showed it was false, so he answered the question. But of course, one wants to understand what is true, and then he did something which I found even much more remarkable. So you can modify the conjecture, and Montgomery quickly did, as I believe did Jean, and that is, you understand that it's no longer an L2 statement, but rather an L infinity to L2 statement, so that we'll assume all the coefficients A, N. His counterexample is then not a counterexample to this. You assume that the ANs are all less than or equal to 1, which we didn't assume before. And then the sum of the AN squareds you replace by n to the 1 plus epsilon. So this refined form seems like it's probably true, and that's the new version of the Montgomery conjecture. It's still very powerful, still implies the density hypothesis. Well, in the same paper, Bourgain shows that this thing implies the Kakaya problem. I mean, what's this got to do with the Kakaya problem? So this was absolutely amazing. So what is the Kakaya problem? If I have a set in RD, any set which contains the translate of any given line. So any line that you give me, I can translate that in RD to a line which is in the set. Then you think that set better be very big. And the conjecture, the Kakaya conjecture, the well-known unsolved Kakaya conjecture, is that the dimension of that set is D, is as big as it has to be. And this is a problem that, I think this may be the first place that Jean really turns to this problem. But he shows it follows from this Montgomery conjecture. So first he shows Montgomery's conjecture is false, he adjusts it, and then shows, well, it's one very powerful conjecture because it implies this. And this Kakaya problem became, I think, Jean's favorite. He told me many times this is the problem he really wanted to solve. And although he didn't solve it, he made all or many of the breakthroughs on the problem that exist today. And with this and his many other works in number theory, I can safely say he scored big. I'll hand over to Avi. Thank you very much.
Hi. Yeah, my mic is on. Okay. Let me just find my talk here. I think. Okay, so I'm just continuing Jean, so I will not, I mean, he gave a wonderful introduction to the director as well to what the presence of Jean here meant, or not just here, but to the mathematical community. He's been my colleague for 20 years, and it, while it was expected, it was still a shock, and for me that he's not here anymore, and it's yeah, just extremely sad. On the other hand, you know, he made us happy so many times. And I want to tell you about some part of his work that I understand well, better than most of the stuff that he was doing. And I'll talk about the sum product theorem and applications of the sum product theorem. The plan is just to tell you the statement of this theorem, and then I want to show you how, you know, it will be very elementary, something that's always, at least in spirit, you can explain it to an elementary school student, and I did, actually. So, and then in the hands of John, it became like an enormously powerful tool, enormously powerful. So you'll see some examples of applications in very diverse areas: combinatorial geometry, number theory, group theory, and extractor theory. I'll explain maybe the terms that some of you don't know here. But anyway, let's see first the statement of this theorem. So there are actually several theorems, and some existed before. And this was the sum product theorem in the reals. This existed before Jean came into the picture. And it's the following very basic statement. So first we fix a field and some subset of this field. And here's what we are interested in. We are interested in what happens when we add up all pairs of elements in the set. Okay, so A plus A is just the sum of all pairs of elements in the set. And A times A is the product of all pairs of elements in the set. So we are trying to understand sums and products, things that everybody understands since second grade. So in particular, we are trying to understand how much bigger is the new sets we construct by adding or by multiplying gets. And while potentially we have quadratically many pairs, sometimes these sets can be very small. For example, where is the laser pointer? Oh, good. If the set is just an arithmetic progression like here, you add all pairs, you get just the numbers between 2 and 2k, so very few numbers. So sometimes you don't get many numbers, even if you add all pairs. And on the other hand, if you take a geometric progression and you multiply all pairs, you again get very few numbers. So if you're not with me, tell me. This is the basic thing. That's what will serve us most. So sometimes sets don't grow under addition and other sets don't grow under multiplication. So is it possible, the basic question is it possible for a set not to grow under addition and not to grow under multiplication? That's the basic question. And Erdős and Szemerédi looked at the case where we are just over the reals. We are just dealing with ordinary numbers, okay? And they proved that this is impossible. There's a fixed epsilon, so that no matter what set you start, what finite set you start with, either it will grow in the exponent under addition or under multiplication. No set can be too close to an arithmetic progression to a geometric progression at the same time. So things happen in the exponent, they'll happen in the exponent for the rest of my short talk. So watch out for these exponents. So again, addition and multiplication are somehow orthogonal to each other. They cannot, they behave differently than each other. No set can remain small both under addition and under multiplication. Okay, so it's an elementary statement, and you stare at it and you say, okay, fine, maybe. So we'll see soon the power of this. But before, and this is about the real line, and where there's room to grow. And the next question we are going to ask, what happens in finite fields? So this is the statement for the reals. And the question is, what happens if we look at a finite field? Well, in finite field, there is no infinite room to grow. So for example, if the set is the whole field, then the statement is false. There is no growth under addition or multiplication. So okay, you say, okay, let's make sure the set is not quite the whole field. There is room to grow. So it's more some fixed power of the field. And then you think a little bit and say, well, this cannot be true either, because maybe the field has a subfield. And if that set is a subfield, then it will not grow. So okay, let's remove this condition. So no subfield. So we are left with prime fields. And that's the main issue here. We are looking at prime fields. And here is a theorem of Bourgain, Katz, and Tau, and some addition of Konyagin. But basically, it says the same thing over a prime field. You have a set, it's not too large. It must grow in the exponent either under sum or under product. Okay, that's the sum product theorem. That's the one that we are going to care about. And again, looks like a statement that's an interesting, maybe curious thing. Yeah, you can explain it elementary to people in elementary or high school, but what? So I'll show you why it's interesting, but I want to say that the first thing that happened, after proving this, by the way, Terry Tao, in the same blog that Peter referred to in the obituary to Jean, he mentioned something about this theorem and how he and Katz were stuck and came to Jean to help them complete the theorem, as like many stories about other results of Jean. Jean took this, and for him it was like many other things he did. It was just the beginning of exploration. And the first thing he did, and then many others after him, was just generalize it. So enormous number of generalizations. I'm not going to talk about them. Maybe you'll hear some tomorrow from Elon about this. But it came to become a phenomenon, not one theorem, but a phenomenon. He called it sum product phenomena, and he wrote dozens of papers on this, on variants of this in other scenarios. I'm not going to talk about this. So I want to tell you about applications to these 4 areas. So let me introduce each. I'll talk 2 minutes about 2 or 3 minutes about each of them. And the good thing, if this one particular area doesn't appeal to you, or you are far from it, then you will recover in 2 or 3 minutes, and we'll go to something else. Combinatorial geometry. What is this area? It's just the study of discrete geometric structures, and the most basic ones are points and lines. And what you are trying to understand is incidences. You have a picture like this, and you are going to count how many pairs of points and lines exist where the point is on the line. Okay, so that's, again, very elementary. And here's the one question you can ask. So we have a set of points, let's call it P, of n points. There is a set of lines, again, L lines. Let's call it L. So like in this picture, n is 7. There are 7 points and 7 lines. And what you are trying to count is the incidences. How many pairs point lines so that the point is on a line? Okay? How big can it be? And just from, many of my slides, we have this before the sum product theorem and after the sum product theorem. It was like, the world changed after this sum product theorem. So before the sum product theorem, first of all, just because every 2 points define a unique line, you can prove this upper bound, that the number of incidences is at most n to the 3/2. And in the reals, it's a very important theorem of Semeredy and Trotter. You can beat this. You can get much better than 3/2. And that's the name of the game. In what situations can you improve this? So over the reals, you can improve it. And this is a sort of, elementary number theory argument. And the question about prime fields was open, and in fact it was in the same paper of Bourgain, Carten, Tau, they solved it, and they improved this 3/2 by an epsilon. Everything happens in the exponent. Again, you might wonder, so why is it so interesting? So again, this really, so it's just the second half of their paper, but in fact it encodes a much stronger statement than the sum product theorem. It encodes a statistical version of it. They don't talk about it, but later it came out that it has this deeper meaning, and in fact it's harder to prove. And we'll see some of these consequences of this statistical version later. So that's a major result in combinatorial geometry, and it has consequences there that I will not talk about. Okay, so that was one area. Number theory. So number theory you saw in Peter's talk, and all over the place in number theory there are exponential sums. And let me show you what the sum product theorem does for exponential sums. And I'm going to talk about very specific one, and then mention some others. One specific oops, is this nice? Maybe I have to start talking or finish talking or do something. Okay. So we are in a prime field, and think of a multiplicative group G in the non-zero elements of F. Okay, so we have a multiplicative group. What we are going to study is, exponential sums are often about that, about the interplay between multiplicative and additive structure, and that, of course, is a power of the sum product theorem there. So, but the problem is elementary. I give you a multiplicative group, and I ask, so we can define the Fourier coefficients of this, the characteristic set of this group. So it's just a sum of the roots of unity raised to this AG over all elements of the group, just a Fourier coefficient at A. And we take the S of G to denote the maximal value of all non-trivial Fourier coefficients. Okay? And it's clear, every element here is at most 1, so the size of this, this maximum Fourier coefficient, largest group Fourier coefficient, is at most the size of the group. That's the obvious bound. And what you want in all exponential sums is to see cancellation, to see. So you want something like bounds of this type. Is there cancellation? Does this, roots of unity mix with each other and become smaller? So this indicates, the cancellation or interaction between additive and multiplicative structure, or some notion of pseudo-randomness, and in fact is very important. So can we get this for groups in FP? And people started working on it, and the main question was, for how small a group can you get such cancellation? And before sum product theorem, people were just, working hard at it, and first did it for groups bigger than square root p, then bigger than p to the 3/7, p to the quarters, and it got harder and harder, and it also stopped. And then Jean came, this work with Koniagin, and basically said it can be as small as you want. Any power of the field, you get some cancellation. So that was already a big, big improvement. And then he went on to generalize it. Maybe I shouldn't read it, not just for groups, but for arbitrary sets. When groups don't grow under multiplications, arbitrary sets do, but you get a bound in terms of this growth. And after this success, Jean just took these ideas of having this amazing hammer of sum product theorem and went to tackle other exponential sums. And one of the important achievements is significantly improving the bounds in the Mordell exponential sum. I'm not going to tell you exactly what it is with the formula, but it extends this Gauss and Weil sums that basically talks about polynomials that are sparse but are of high degree, for which standard methods did not do anything. So, so there's this and other words that I'm not going to talk about. All right, that was the slide on number theory. Expander graphs. What are expander graphs? Expander graphs are, this is an example, are graphs that are sparse, namely every point is connected to a few points, here to 4 other points. But the number of vertices is large. Here it's 17, but you should think 1 million, 1 billion, 1 trillion, still of degree 4. So you want sparse graphs, but you want them, despite sparsity, despite having very few edges, you want them to be highly connected, very hard to cut. They should have short diameter. Distances between 2 points should be short. There should be, the random walk on such a graph should rapidly mix, get to a random place. If you look at the Laplace operator, should have a spectral gap. It turns out that all these 4 demands are essentially equivalent. Again, this that's already an intricate. You know that something is fundamental when it has various different descriptions that are all equivalent. But this is one of the most amazing objects to have if you have your hands on it. In fact, in computer science, you cannot go anywhere without a few in your pockets, because in every area of computer science, there are applications of expanders. And maybe more strikingly, because this is a discrete structure, it has application in all these areas of mathematics. So it's one of the most universally applicable objects. So the question is, do we have them and how to construct them? So here I want to talk just about the group theoretic constructions, how the group theory mixes with the expander theory, and the explanation goes through, group theory suggests very nicely graphs. These are Cayley graphs. What are Cayley graphs? If you have a finite group H, and T is a set of generators of H, then you can build a graph in an obvious way. You take, that's the Cayley graph. The vertices are the group elements, and two are connected if you can move between them using a generator. So they are very, so if T is small, then it's a sparse graph. You may be interested in the diameter of this graph, how far are points from each other, in the spectral gap of the random walk on this graph. And it turns out that one definition of an expander is that this, well, you have this gap, or the second eigenvalue of the random walk is strictly less than 1. And this implies that the diameter is small. So there were basic questions about, which groups and which generating sets give you expanders, and questions about which such Cayley graphs have small diameters. I'm not going through the conjecture. Let me tell you, well, first I'll just focus on one group, just the group of 2 by 2 matrices with determinant 1 over prime field, so SL2P. And in this group, before the sum product theorem, there were lots of results showing that some generating sets, some specific generating sets, will cause this Cayley graph to be an expander. Okay, so even with just 2 generators, but specific ones, it will become an expander graph. So Selberg, Lubotsky, Phillips, Sarnak, Montgomerys, Sarnak and Shu, and others just knew that some generating sets, specific ones, will make these graphs expanders, and people conjecture that they, it should expand in many more situations. And using sum product theorem, Peter started mentioning it. First came a result of Helfgott, again using sum product theorem, that showed just that the diameter is small for any generating set. And Jean saw this, and immediately, this with Gambourg, knew that he has gold in his hand, and together with some ideas from the Sarnak-Shu paper, they wrote this first paper proving that basically for any pair of generators, pick them at random, you'll get an expander. Or in fact, characterize, if these 2 generators don't generate a cyclic group, then it will be an expander. So basically, they solve the problem for this particular group. And then, I would say, not all, can you say all paradise broke loose instead of all hell broke loose. Jean and then others improved it and proved similar results for all finite simple groups. Bourgain and Gambourg extended it to non-finite groups like unitary groups, and then Bourgain Yehudayov to non-compact groups, and then that implied very important results in expander theory that I'll not define. And it also led to this affine sieve that Peter mentioned, together with some Bourgain, Gambourg, and Sarnak, where they use search for primes in the orbits of arithmetic groups. God knows why. And in fact, even Jean didn't know why, but he trusted Peter. Okay, so last topic, randomness extractors or randomness purifiers. That will be just one picture to end. This is another amazing pseudo-random object, randomness extractors, that already has as many applications in computer science as expander graphs, and they are related in some non-trivial way as well. I must say that I don't know, real good applications in math, although Elon Lindenstrauss had some ideas in dynamics and ergodic theory. But anyway, I'm sure there will be. So watch out for them or start working on them. So I'll tell you in pictures what extractors are and how some product comes into that in the last 2 minutes. I want to talk about weak random sources and what extractors mean. So before that, I'm sure you all know that having, lots of coin flips, randomness, pure randomness, perfect, unbiased, independent coin tosses is very powerful. It's powerful in statistics, in cryptography, in algorithms, in game theory, in gambling, you name it. And in all these applications, whatever application it is, the way it's analyzed is here is what will happen if we had perfect coins. Then wonderful things happen with very high probability. And then you ask yourself, okay, great, but where do we get perfect random bits from? And, you say maybe from the real world. The real world, of course, we don't understand it so well, especially the randomness in it. But we definitely, know from experience that there are various things in the real world that we cannot predict too well, right? The weather, maybe the stock market, various physical phenomena. We may have some idea. We may have, maybe we know the weather tomorrow with 99% probability, or we know what will happen to the Microsoft stock with some probability, and we might want to gamble or not. So there are unpredictable things, but they are not like any, independent coin tosses. They are very dependent, very correlated, very biased. So can you do something with them? Can you get the results of any of the applications with really lousy random coins? And this is what extractors do. Extractors are there to convert such lousy random coins or tosses, distributions that have some entropy in them somewhere, but are far from being the uniform distribution, extract from them the uniform distribution and then use it in the application. That's what extractors are, very informally. And I'll tell you just one application of the sum product theorem to the construction of extractors, and this is in the case that you have several of these weak randoms, so you have a few random sources that they are independent from each other. You must remember that people believe that sunspots affect the stock market, but let's say they don't. They have a few. And then using sum product theorem, in fact, maybe this was the first application because I was working on a problem with these colleagues, Barak and Impagliazzo, and we were stuck. And then Jean gave at the Institute the first lecture on the sum product theorem. And we came out, basically said, it solved our problem. So what you do, you want to somehow enhance the entropy of this lousy distribution, you mix sum and product. And you do it a few times and it works. That's basically it. In fact, you use a statistical version of the sum product theorem. Jean himself, got really interested in extractors and proved, built new extractors for various types of weak sources, affine sources, two sources, and so on. And it, went off from there. I should say that the best results eventually are not using sum product theorems. Anyway, let me conclude. So, I was thinking, giving this kind of talk, I should say something about Jean's secret of success. And you can do it in various ways, but one way is to you can ask anybody about their secret of success. One way to do it is to ask people to complete this sentence. If I've seen farther than others, right? So you all know what Isaac Newton said, right? I'm sure you all know. Anybody who didn't? Okay, so you know. It's because I stood on the shoulders of giants. How many people know what Murray Gell-Mann, a Nobel laureate in physics, said? All right. So he said it is because I was surrounded by... So, well, you probably know. I just know this quote, and I don't know if he just had a great sense of humor or he had a huge ego or both. Both, okay, yeah. So what would John say to this? I mean, he told me this many times, not in this complete sentence, but it was like Jean is always very, very concrete, very straightforward. He said, it's because I combine analysis and combinatorics. That was his honest answer many times. So, thank you.